Welcome back to the Deep Dive.
Mm.
Today, we're tackling something huge in the AI space. The meteoric rise of AI agents. It's not just talk, right?
Not at all. We're seeing over half of large IT companies actually using them now.
And the market projections are just staggering.
Yeah.
From, USD 5.2 billion now to potentially almost USD 200 billion by 2034. That's huge.
It really is. And, the bedrock for most of these agents currently, it's large language models, LLMs.
Right, the big ones. They're making the decisions, running the operations, doing the reasoning.
Exactly. The whole operational model is kind of deeply ingrained around using LLM API endpoints. And that's led to some, substantial capital bets.
Substantial is one word for it.
Sure.
I saw the numbers for 2024, something like $5.6 billion for the LLM API services themselves, but $57 billion invested in the cloud infrastructure to host them. That's a massive difference.
It's a tenfold discrepancy, spending 10 times more on the infrastructure than the actual services running on it.
And that whole investment model really hinges on one big assumption, doesn't it?
Yeah.
That this LM-centric way is the way, the future.
Precisely. And that's where today's deep dive really gets interesting. We're digging into this, frankly, groundbreaking paper from NVIDIA Research and Georgia Tech.
Okay.
And it challenges that exact assumption, their core idea. It's bold. They argue that small language models, SLMs, are actually the future of agentic AI.
Okay, SLMs. Before we dive deeper, let's get the definition straight right from the paper. What do they mean by an SLM? A small language model.
So they define an SLM as a language model that's, small enough to fit onto a common consumer device, think your phone, your laptop.
Okay.
And it needs to run inference, do its calculations, fast enough for a single user's agentic requests. Low latency is key.
Got it. Fast enough for real-time use on my device. To give a size estimate.
Yeah, they suggest that as of 2025, models under about 10 billion parameters would probably qualify as SLM.
Okay, that makes sense. So
Yeah.
smaller, local, fast.
Yep.
And an LLM then is just anything bigger.
Basically, yes. Any language model that doesn't meet that SLM definition. The ones typically needing that big data center infrastructure we were just talking about.
Right. And they use agent and agentic system pretty much interchangeably.
Yep. Just referring to these AI systems built for specific tasks.
Perfect. Okay, definition's clear. Let's get to the core of their position. What's the central claim? Why SLMs?
They lay out this value statement based on 3 core assertions. Let's call them V1, V2, V3.
Go.
So V1, SLMs are sufficiently powerful. They argue these smaller models can, in principle, handle the language tasks needed for agented applications. They can actually do the job.
So capability isn't the issue they're claiming. Interesting. What's V2?
V2, SLMs are inherently more operationally suitable for agentic systems than LLMs. This is about the practical side, deployment, integration, how they fit into the workflow. They argue SLMs just fit better.
Okay, powerful enough, better suited operationally.
Yeah.
And V3. I'm guessing this involves cost.
You guessed it. V3. SLMs are more economical. For the vast majority of tasks language models do in agents, they argue SLMs are just necessarily cheaper to run because, they're smaller.
Powerful, suitable, and cheaper. That's a compelling trio. What's the sort of pragmatic thinking behind this?
The paper points out that most tasks agents do aren't these grand, open-ended conversations. They're often repetitive, very specific, scoped things.
Like what?
Like extracting a specific piece of data from a report over and over, or calling a software tool with precisely formatted input. For those kinds of jobs, SLMs aren't just good enough. They're often better.
Better how?
Lower latency, fewer resources needed, and yes, significantly lower operating costs. The analogy they might use is, you don't need an 18-wheeler truck for a local delivery.
Right. Makes sense. And this leads to the idea of heterogeneous systems.
Exactly. Heterogeneous agentic systems. The vision isn't necessarily only SLMs, but systems where SLMs handle the routine, specialized stuff by default.
And the big LLMs.
They get called in selectively and sparingly. Only when you really need that heavy-duty general reasoning or maybe complex open-domain dialogue. It's about using the right tool for the job.
So combining the strengths, the precision and efficiency of SLMs with the generality of LLMs when needed.
Precisely. It's a modular approach. And interestingly, they even touch on the broader picture.
Oh, like what?
They frame this shift almost as a sort of Humean moral ought, a responsibility.
And moral responsibility. Why?
Because of the rising infrastructure costs and, importantly, the environmental concerns around running these massive LLMs in huge data centers. They suggest moving towards more efficient SLMs isn't just smart, it's arguably more responsible AI deployment.
Wow, okay, so it connects to sustainability too. That's a powerful angle.
It is. They're saying this could be a greener path for AI's future.
Okay, that's a strong case for why SLMs should do the future.
Uh-huh.
But let's dig into the evidence. The paper lays out specific arguments, right? Starting with argument A1. SLMs are already sufficiently powerful. Is that really true now?
Well, here's what's fascinating. Yes, scaling laws exist. Bigger models tend to be better overall, but the paper highlights that the relationship, the curve between size and capability, is getting increasingly steeper.
Meaning?
Meaning newer SLMs, often with better architectures or training data, are getting much closer in capability to older, much larger LLMs than we previously thought possible. The gap is closing, and vast.
Okay, steeper curve.
Yeah.
Any specific examples that really drive this home?
Oh, absolutely. Look at Microsoft's Phi series. Phi 2, it's only 2.7 billion parameters. Tiny compared to the giants.
Right.
But it's performing on par with LLMs that have around 30 billion parameters. And it does it roughly 15 times faster.
15 times faster with comparable results?
Yeah.
That's incredible.
And it doesn't stop there. Their newer Phi 3 small model, 7 billion parameters, is reportedly competing with models in the 70 billion parameter range.
So we're seeing order of magnitude improvements in efficiency for similar capabilities.
Exactly. It's not just incremental gains. And there are others, like the DeepSeek R1 Distill Quen 7b.
Okay, what about that one?
That model has actually outperformed some really large, well-known proprietary models like versions of Claude 3.5 and GPT-4o on specific common-sense reasoning benchmarks.
Wow. An SLM outperforming the big names on certain tasks.
It really hammers home their point. Capability, not the parameter count, is the binding constraint. What matters is what it can do.
Okay, that's a very strong case for capability. Let's move to the economics.
Yeah.
Argument A2. SLMs are more economical. This feels like a really crucial point for adoption.
It's huge. The paper estimates that serving inference for, say, a 7 billion parameter SLM is anywhere from 10 to 30 times cheaper than a big 70 or 175 billion parameter LLM.
10 to 30 times cheaper. In what terms?
Across the board. Latency, so faster responses, energy consumption, so greener and cheaper power bills, and FLOPs, the actual computational work needed. It just takes vastly less effort to get an answer.
Which enables things like real-time interaction much more easily.
Definitely. And it's not just about running inference. What about customizing them? Fine-tuning.
Right. Fine-tuning LLMs can be incredibly expensive and slow.
Exactly. But with SLMs, they highlight the agility you get from techniques like PEFT, parameter efficient fine-tuning, things like LoRi or Dora.
Yep.
These methods let you fine-tune an SLM in maybe just a few GPU hours, not days or weeks.
Few hours. So you could adapt an agent-specific skill almost overnight.
Potentially, yeah.
Yep.
It allows for rapid specialization and iteration. Plus, this efficiency opens the door to running them locally.
On the edge, like on my actual computer.
Precisely. Running locally on consumer-grade GPUs. Think NVIDIA's ChatRTX as an example platform. This means lower latency because the model's right there, and potentially much stronger data privacy and control because your data doesn't have to leave your device.
Local control is a big deal for many users and companies. The paper also mentioned something about parameter utilization. Like SLMs use their parameters more efficiently.
Yeah, it's an interesting idea. Think about a massive LLM. It has, billions and billions of parameters. But for any single calculation, only a fraction of those parameters might be actively involved or activated. With an SLM, because it's smaller to begin with, a larger proportion of its total parameters might be actively contributing to the result for any given task. So arguably, they might be fundamentally more efficient in how they use their computational resources. Less waste, perhaps.
Less computational overhead for the same output quality on specific tasks.
Potentially, yes. And this all feeds nicely into the idea of modular system design.
The Lego analogy you mentioned earlier.
Exactly. Building agentic intelligence not from one giant block, but by composing smaller, specialized SLM bricks. The paper argues this leads to systems that are cheaper, faster to debug, easier to deploy, and better aligned with the diverse needs of real-world agents.
More flexible, more maintainable. Okay, that makes a lot of sense. Now, the paper also brings up how agents use these models. Arguments A4 and A5, I think. Agents expose only narrow LM functionality and agentic interactions necessitate close behavioral alignment.
Right. This is about the reality of agent workflows. Agents aren't typically built for free-form chats. They usually have very specific goals.
So the prompts are very structured.
It's extremely structured. The paper talks about tediously written prompts, and meticulously orchestrated context management. Essentially, developers spend a lot of time forcing a generalist LLM to act in a very narrow, specific way for a particular subtask.
Kind of like using only one tiny corner of a giant workshop.
That's a good way to put it, and for that tiny corner, the paper argues, an appropriately fine-tuned SLM would suffice. It doesn't need the rest of the giant workshop.
And it might even be better, the alignment point.
Yes, especially for things like tool calls or generating structured output like JSON or XML, agents often need outputs in a very strict format to work correctly.
If the format's wrong, the whole process breaks down.
Exactly. A specialized SLM trained specifically to always output in that one required format is likely much more reliable than a general-purpose LLM that might occasionally hallucinate or just get the format slightly wrong. SLMs offer better behavioral alignment for these specific constrained tasks.
Reliability is key for agents.
Okay.
And argument A6 connects back to the heterogeneous idea. Agentic systems are naturally heterogeneous.
Right, it just reinforces that agent architectures are already well-suited to mixing and matching models. You could have an LLM as the main controller or router.
The brain of the operation.
And then it delegates specific language tasks, maybe summarizing a document, extracting info, handling a simple dialogue part to specialized SLMs. It fits the diverse nature of agent tasks in the real world.
Makes sense. And the last argument, A7. Agentic interactions are natural pathways for data gathering. This sounds like a self-improvement mechanism.
It really is. Every time an agent uses a language model or calls a tool, that interaction, the prompt, the response, the tool parameters, maybe even user feedback is potential training data.
Data generated naturally just by using the agent.
Exactly. High-quality organic data. And this data can be collected and used to further fine-tune an expert SLM for that specific task, making it even better and, crucially, potentially lower the cost of that call in the future.
So the more you use the agent, the better and cheaper the SLM components can become. A continuous improvement loop built right in.
That's the idea. It's a very powerful concept for evolving agent capabilities efficiently.
This is fascinating stuff. But, no argument is completely one-sided. The paper acknowledges alternative views, right? How does it address the pushback?
It does. It tackles three main alternative viewpoints. The first, AV1, is probably the most common. LLM generalists will always have the advantage of more general language understanding.
The bigger is better argument again, based on scaling laws and this idea of a semantic hub.
Right. The thinking is that LLMs, due to their size, develop a more comprehensive, abstract understanding of language, this semantic hub, that smaller models just can't replicate.
So how does the paper counter that? They have rebuttals A through A11, I believe.
They do. First, A8, they point out that scaling law studies often assume the model architecture stays the same, just gets bigger. But recent SLM research shows you can get distinct performance benefits from architectures specifically designed for smaller scales. It's not just about shrinking an LLM design.
So architecture matters, not just size.
Second, A9, the flexibility of SLMs means you can easily fine-tune them for specific tasks to get the reliability you need. General scaling studies don't usually account for this task-specific tuning potential.
Right. The benchmarks measure general ability, not specific tune performance.
Yeah, exactly. Third, A10, they mention you can scale SLMs at inference time for reliability if needed using techniques like self-consistency, often still at a lower overall cost than using an LLM. And finally, A11, getting back to agentic systems.
Yes.
Because agents break down complex problems into simpler subtasks, that supposed general abstract understanding due to the hub in an LLM often becomes of little utility for the specific narrow task an SLM is asked to do. The problem is already simplified.
So for the specific job the SLM is doing, that big picture understanding might be overkill or irrelevant anyway.
That's the argument.
Okay, what's the next alternative view? AV2. LLM inference will still be cheaper because of their centralization.
Yeah, the argument here is operational. It's potentially harder to manage and efficiently utilize lots of different specialized SLM endpoints compared to just hitting one big centralized LLM API. Plus, people sometimes forget the costs of setting up all that SLM infrastructure and hiring specialized talent.
Those sound like fair practical points. What's the rebuttal? A12, A13.
The paper acknowledges these challenges but points to two trends. First, A12, there have been significant recent improvements in inference scheduling and large inference system modularization. Tools like NVIDIA Dynamo are specifically designed to make managing diverse model endpoints more efficient.
So tooling is catching up.
It seems so. And second, A13, they note a consistent falling trend in the costs associated with setting up infrastructure in general. So while it's a cost, it's becoming less prohibitive.
Okay, so the operational challenges are being addressed. And the last one, AV3. Industry inertia favors LLMs. This isn't technical, it's about momentum.
Right. It's the simple fact that the industry has already invested heavily in LLMs, built tooling around them, trained people on them. There's just inertia.
People stick with what they know.
Exactly. The paper calls this a distinct possibility. They don't dismiss it. But they strongly believe that the weight of advantages for SLMs, all those arguments from A1 to A7 we discussed, is compelling enough that it can plausibly overturn the present state of affairs. The benefits might just be too large to ignore long term.
So if the case for SLMs is so strong, technically and economically, why aren't they everywhere already? The paper covers barriers to adoption, right? Yeah. What's holding things back?
They identify three main barriers. First, as we just touched on, B1, large upfront investment into centralized LLM inference infrastructure. A lot of money and effort has already gone into the LLM ecosystem.
Path dependency. Hard to switch tracks once you've laid down miles of rail.
Pretty much. Second barrier, B2. Use of generalist benchmarks in SLM training, design, and valuation. This is crucial. SLMs are often developed and judged using the same broad benchmarks designed for LLMs.
But that's not where they necessarily shine brightest.
Exactly. Those benchmarks often don't capture their strengths in specific, narrow agentic utility. So they might look less impressive on a general leaderboard, even if they'd be perfect for a particular agent task. We need better, more task-specific benchmarks for SLMs.
We're measuring them with the wrong yardstick. What's the third barrier?
B3. Lack of popular awareness. Simply put, LLMs get all the headlines, the marketing intensity, and press attention. SLMs, even if highly effective for certain jobs, just aren't as well known or hyped up.
So investment inertia, the wrong benchmarks, and less visibility.
Yes, but the paper is quite clear. These are seen as practical hurdles and far from being fundamental flaws of the SLM technology. They believe these barriers can be overcome.
Okay, so how do we overcome them? To help bridge that gap, the paper actually proposes a practical method, doesn't it? An LLM to SLM agent conversion algorithm, like a recipe.
Sort of, yeah. A 6-step process designed to make the transition from using LLMs to using SLMs and agents relatively painless.
Okay, let's walk through it. Step 1.
S1. Secure usage data collection. You need to start by understanding how the LLM is actually being used in your agent. So, deploy logging to capture the prompts, the responses, any tool calls, latency, etc. for non-interactive agent calls. And crucially, do it securely encrypted logging anonymization.
Got it. Log everything the LM does for the agent securely. Then
S2. Data curation and filtering. Collect enough data, they suggest a rule of thumb of maybe 10,000 to 100,000 examples for fine-tuning. Then rigorously clean it up. Remove sensitive info, PII, PHI, using automated tools or maybe paraphrasing techniques.
So get lots of clean, relevant, anonymized data. What's S3?
S3. Task clustering. Now you analyze that data. Use unsupervised clustering algorithms on the prompts and the agent's actions, like the responses or tool calls, to find recurring patterns.
To see what kinds of specific tasks the LLM is doing repeatedly.
Exactly. This helps you identify candidate tasks that could potentially be handled by a specialized SLM. Maybe it's always doing intent recognition from user input, or extracting data for a specific tool, or generating a certain type of code snippet.
Okay, you've identified the potential SLM jobs. Step 4.
S4, SLM selection. For each task cluster you identified, you choose one or more candidate SLMs. You'd pick based on their known capabilities, how they perform on relevant benchmarks if available, their licensing, and critically, their deployment footprint. Can it run where you need it to?
Makes sense. Match the SLM to the specific task, then S5 must be training.
S5, specialized SLM fine-tuning. Yep. You take the data specific to that task cluster, prepare it as a training data set, and fine-tune your chosen SLM. Again, leveraging efficient methods like PE, FT, LoRa, QLoRa is recommended to keep costs down. You might even use knowledge distillation to train the SLM to mimic the LLM's outputs for that task.
Okay, train the specialist. And the last step, S6.
S6, iteration and refinement. This closes the loop. You need to continuously monitor performance, collect new usage data, and periodically retrain the SLMs and any models routing tasks to them to keep them accurate and adapt to any changes in how the agent is used. It makes it a living system.
That connects back to argument A7, the continuous improvement idea.
Precisely. It's a cycle.
That sounds like a really practical, actionable plan. To make this even more concrete, the paper's appendix includes some case studies, right? estimating the replacement potential in real open-source agents.
Yes, they looked at a few. For instance, MetaGPT, which is a framework for creating multi-agent systems, they estimated that around 60% of the LLM queries it typically makes could likely be handled reliably by SLMs.
60%. What kinds of tasks?
Things like routine code generation based on specific inputs, or generating structured responses that follow a template, repetitive stuff.
Okay. Any other examples?
They also looked at Cradle, which is an agent designed for controlling a computer GUI. Their estimate there was even higher, potentially 70% of its LLM calls could be shifted to SLMs.
70%. Wow. For things like
Repetitive GUI interactions, clicking through sequences that the agent has learned. Again, tasks that become fairly predictable and scoped once learned.
So these aren't just theoretical savings. In real-world agents, there seems to be a substantial chunk of LLM work that could potentially be offloaded to more efficient SLMs.
That's exactly what these case studies suggest. It supports the core argument that a lot of current LLM usage in agents isn't strictly necessary and could be done more efficiently.
Okay, this has been incredibly insightful. So to wrap this all up, the central message from this NVIDIA and Georgia Tech paper is pretty compelling.
It really is. The argument is that the future of AI agents looks likely to be powered in large part by small language models, not just giant LLMs.
Because SLMs are becoming powerful enough, they're operationally a better fit for many agent tasks, and they offer significant economic advantages.
Exactly. Especially for those specialized, often repetitive tasks that make up the bulk of what many agents actually do. The current LLM-first model might be powerful, but the paper argues it's often inefficient and maybe not sustainable long-term, given the costs and energy involved.
And for you, our listener, why does this shift matter? Well, it points towards a future with potentially more cost-effective AI agents. They might run faster, be cheaper to use, maybe even run locally on your own devices, offering better privacy.
It could change how responsive and accessible AI agents feel. And it raises a final thought to consider.
Go on.
Beyond just efficiency, what are the broader ripple effects of this potential shift? If powerful AI capabilities become more accessible through smaller, easier-to-deploy SLMs, what does that mean for the democratization of AI?
Could it spur more innovation from smaller players? Reduce bias by enabling more diverse models?
Perhaps. And how might your own daily interactions with AI change? Imagine agents running seamlessly on your glasses, your watch, your car, powered by these specialized little models. It's a fascinating future to contemplate.